Good morning, everyone. I'm Priyanka. I'm here to introduce today's speaker, the session 3, Memristor Applications with Analog Neural Networks by Professor Alex James. Professor Alex James received the PhD degree from the Queensland Micro and Nanotechnology Centre, Griffith University, Brisbane, QLD, Australia. He works in the broad area of brain-inspired circuits, permissive systems, analog circuits, and imaging systems. He is currently a dean and professor of AI hardware at Digital University, Kerala. He is actively engaged in research, commercialization, and startups, and is professor in charge of Maker Village that supports over 80 plus hardware startups. He is a chief investigator of the Center for Intelligent IoT Sensors and India Innovation Center for Graphi, developing new products to the market. Dr. James was the founding chair for IEEE Kerala section, Circuits and Systems Society. He is a member of IEEE CAS Technical Committee on Non-Linear Circuits and Systems, IEEE CT-SOC Technical Committee on Quantum in Consumer Technology, and IEEE CT-SOC Technical Committee on Machine Learning, Deep Learning, and AI in CE. He was an editorial member of Information Fusion elsewhere and is an associate editor for IEEE Access, IEEE Transactions on Emerging Topics in Computational Intelligence in 2017 and 18. And Sir is also an IEEE Transactions on Circuits and Systems editorial member from 2018 to till date. He is a senior member of IEEE, life member of ACM, senior fellow of HEA, fellow of British Computer Society, and fellow of IET. We welcome you, sir, on behalf of ICMACC conference. Sir,
Thank you.
yeah.
Let me share the screen. Is it visible?
Yes, sir.
Okay. Can see my screen, right?
Yes, sir, it's visible. Can you just make the presentation in presenting mode, sir?
Yeah, I'm doing that. Okay. Is it visible?
Yes, sir, perfect.
Okay. So, in my talk, like today, what I'll try to do is I'll try to give a overview of the analog computing as we see today, and then take it to the Memristor system, so that you get a idea of why we do that, or why we need to think about like Memristor computing. So as a bigger picture, you can contextualize the whole thing in terms of what Industry 4.0 today needs, and you can see automation, big data, cloud computing, or autonomous systems, IoT, data management, all of them increasingly becoming important with more of AI and related techniques coming in the industrial sector. Now, if you take an example of that technologies like say big data, and try to relate it to various things that has happened over the last 3 or 4 decades, you can see one very interesting fact that as the transistor technologies, the size of the transistors started to decrease, you could see the computing capability of the devices that we have to increase quite in a non-linear way. So while we say big data, the underlying reason why big data has been of more and more interest is because there are several enablers which helped it to grow. And at the core of it is the hardware technologies that really change the game. So if you see the size of transistors and the processing architectures and all those things, they did not change quite a bit in the 80s and 90s. You could see a lot of architectural level innovations, but it was always being pushed back by the size of the transistors, how much transistors you can pack, or transistor density of the chips itself. which kind of significantly changed in the 20s with the 2000 and after, where you could pack more logic and memory onto the single chip, and thereby reducing the overall space requirements. So you could have like a mobile device having much more power than a computer in 90s, which is a very obvious like thing that you could see. But not so obvious is the servers and other things. You might be using it a lot, but without realizing how much dense capacities have been like built over the years. Compute capability have significantly increased. The architectural changes, many of the proposals which are there in the 90s started to get realized in the 2000s. And things like deep learning, various kind of ML algorithms, all of these could be accelerated, or the computations related to that could be implemented at large scale. So that kind of gives you a sense of where we are going. But what happens today, if you look at, is beyond a point, like scaling the transistors are not giving the kind of advantages it used to give, whether it's the cost factor or the power related issues or energy consumption and all those sort of things. So more kind of innovations are required both at the device level as well as like the kind of architectures that one would use. And the scaling, if you look at, mostly has been with transistor scaling. It's the digital technologies or digital designs that got scaled. Whereas if you have like a processor with analog, or if you have like a mixed signal process, they still have a lot of challenges in terms of truly making use of the scaling capabilities of the transistors, mainly due to leakage currents, or it could be the parasitics that would, or even the sensitivity of the circuits which gets designed. They all become like kind of an important factor as we see further. And another correlation that you could see is with the transistor sizing and the number of AI studies. Clearly, like as you would imagine, if you have like a better compute and better, larger memories to use, obviously you could test out a lot of different types of like neural network applications. And that's what people have been doing. There has been a gradual and a big shift from pure algorithmic level work in AI to more applied or like application oriented work, which has pushed the number of like even like publications and others in this area in the last like decade. Now, when it comes to computing, you can see there are, with the traditional GPU and CPU computation, there are a few major bottlenecks. One is the Moore's law itself being like a challenge. The more you put energy and effort in terms of like matching it with Moore's law, you're looking at like a large cost of production. So a chip, a 1 centimeter square chip with 180 nanometer versus like 7 nanometer or 5 nanometer, or now we are talking about 3 and 2 nanometer. The costing is like, quite exponentially different. Another issue you see is like the memory wall, another is a heat wall. Both of them basically like limiting the speed and the functionality of the GPU and CPUs that are there. On the other hand, what we really need is big data processing, IoT. There is a whole range of like computing required in IoT. Then there is like cognitive related computing, and that's where you can think about like neuromorphic computing or in-memory computing and related things to play a major role, as opposed to thinking about chips which are for GPUs and CPUs. Now, and most of our AI-related works or ML-related works, it's trying to emulate intelligence in various forms. And there are many ways to actually go into that. Like one could be mimicking the brain. Um, so how we go about like computing things in our brain, we could try to mimic that in a chip. So that could be one way to achieve like intelligent computing. But some of the things we need to then worry about, like, are we doing it in an efficient way? For example, the energy consumption, the power requirement needs to be very, very low. So this is not typically easy. So one would need to really compete with how much power a neuron takes in the brain, which is extremely small compared to like a typical neuron which is implemented on a chip. So something of the order of like 4 or 5 difference is what you are seeing. So milliwatts to going down to femto levels, like it's not a trivial problem that people have been trying various methods and different approaches to reduce that. Now, thinking about cognitive architectures is another way, like seeing the whole computing, the way we would see the brain computation. One could think about functional like modeling of those brain computing or functions of the brain to be like mimicked. Or one could look at like the biology specific things and try to like mimic each blocks in the brain. So either way, there are several cognitive architectures over the years that people have come up with, and not all of them may be directly translatable to the to a hardware, but at least like some of them can be converted to like realistic, useful like hardware. And you could see other things like, rather number crunching, like when it comes to many of the AI techniques or like the intelligence per se, if you look at it, it's all about like patterns, how the patterns are generated, how the patterns are matched, how they are dynamically like changing. So those factors needs to be taken into account when designing such a system. So it's never going to be like a static system that you're looking at. You're looking at like a dynamic system, which would learn, which would change, which can understand like patterns in noise and so on and so forth. So usually brain doesn't try to remove the noise. It tries to, it can see the noise as well as it can ignore the noise to focus on the objects. So they're definitely like, it's not like something that you have like a noise filter which would remove things. It does a bit more complex processing than that. And at the same time, one needs to worry about extremely low power and what is being compute. That should be a there should be some kind of self-awareness. So it's not like, you just go about computing everything as we do today, like in GPUs, and you have a pattern, you compute everything about it. So if you look at the brain carefully, you would see sparsity of computation or sparse processing is an important function. Stochasticity that you observe, it's an important function. In most of these operations, what it does is it removes or excludes a lot of like information that is not really required for processing at that stage. So a certain level of like self-awareness in what needs to be computed, what does not need to be computed, has to be incorporated into the hardware system itself. And there are many ways in which you can go about it. You can see as of today, like some of the promising technologies out there, quantum computing, you can see molecular electronics, spintronic being used, 2D materials being used. You can see beyond CMOS technologies being explored, neuromorphic computing. So the ones that I marked there, like that's what I personally think like these would have like much more bigger role compared to the other ones, because other ones may take a bit more time. Although beyond CMOS and extended, there are several technologies, but it may not be well suitable for neuromorphic computations. So something like intelligent computing, as the name itself, neuromorphic, it's mimicking the various kind of neurons or neural networks, which can be both implemented analog, digital, mixed whichever way you can try to implement in the system. So neuromorphic definitely is one of the ways that you could go further. Then the exploration of 2D materials to make the devices to be better or the electrodes to be better, they all will help quite a bit. Alternatively, you can also look at like combining this with like technologies such as quantum computing to improve or speed up the learning and other things, which is typically required for large scale intelligent computing. There are also like other approaches to make sense of the world around us. And in a good part of the intelligent computing itself is being aware of what is the environment in which it needs to be operated, which a processing unit alone will not be able to take care, but instead you would need like some additional mechanical systems or packaging and things like this, which would help to understand the environment in which it will operate. And there is a whole class of intelligent 2D materials and others which could be used for this purpose, from mobile devices to various like larger devices. They could be adapted and integrated with the compute units to ensure like intelligence is like mimicked or realized in a robust way. Why do we need like analog computing, or what is analog computing? So if you just look at like what is analog computing, you would see a traditional like multiplication, addition, subtraction, or division operations. When you do that, can be counted as part of analog. There is no conversion happening. I mean, the computation here is purely in the analog domain, or at first it can be a discrete analog domain. You can also think about like more complex linear operations other than like multiplication, addition operations. You can think about nonlinear operations to be implemented. You can think about like linear and nonlinear functions to be implemented. The idea is like, you don't need to go for a binarization or data conversion to do a lot of these processing. So where does it really fit into as of today? If you look at current literature, most of the work goes into near sensor computing, less into a full-fledged processor. In most of the processors today, you would see blocks of it is getting implemented. Mainly because the output or the interaction in the world at which like those processors sit, they are mostly in a digital ecosystem. So because of it sitting right in the middle of digital ecosystem, always there needs to be a conversion from digital to analog, which may not really show its full potential. How or advantages of having it, but when you place the same like analog process systems next to the sensor, you would see that you save a lot on processing. It improves the speed, accuracy, and many other things. So that's what near sensor analog computing, mostly the signals itself, like input signals that you would have, they're natural. There is a less issues of signal attenuation, noise buildups are less. You have reduced impact of noises. You can perform like more complex operations like MAC, analog MAC, and computational, reduce the computation blocks required to implement those. You can save on power and chip area and things like that. MAC is a multiply and accumulate operation, which is typically what you need in for neural networks. Now, other question one can think about it, okay, near sensor, it makes sense, but what about like thinking about for cloud? Now the thing with the cloud is you can see that most of the things that you would be doing, there will be some kind of computation or some kind of like memory access storage and things like that. Now computations As such, if you look at the implementation part, like implementing a multiplication, you have so many different ways in which you can implement a multiplication in digital system. So depending on the kind of like implementation that you have, you would save on power, energy, and all those factors. Now, on the other hand, if you are looking at like, can we do this in analog? There's nothing stopping us from doing it, but the question is, will it be accurate? So many other times, like you want to do a mathematical computation and use a analog processor to do this, the challenge will be there may be some errors coming because of the parasitics or because of the way in which the circuit itself or the chip itself is designed, the EMI issues and all those things that come by, all of these might actually affect those. So still the question that one would ask is it still what you call kind of feasible? The answer to that is like depends on range of things that you want to do. So it has been shown that you can do like linear system, solving linear systems with like analog computing or analog circuits. But there is always like a issue of like accuracy and other things that come by. And this is basically not that easy to deal with all the time. In some applications, those kind of computations are perfectly to go with. In some others, they're not. So one needs to really look at like where it can be very effective. Then the alternate question that one would ask is, okay, if brain memories are purely analog, the way in which like our mind works, which is more like a functional functionality of the brains being used, why can't we then do it in analog? Because in anyway, like most of those functions that we are trying to achieve through computing, apart from a small set of tasks, like most of the tasks are something that we could do with our brain. So what is stopping us from creating rules and systems around it? And that leads to the question of why not create like a hyper performance computing in analog itself. One solution to that is to not think the whole computation as purely like a deterministic thing, but see it in terms of like statistics and probability. And once you start doing that, like many forms of analog systems can be implemented, and you can also derive and see that like even the digital implementations of what we have is like a subset of like analog systems that we have. So thinking about like that, one could think about like analog memories. You could think about like analog computing. Analog computing will be good for pattern processing, recognition, and things like this, whereas memories could pack much more than a digital memories that are out there. You need not, for most or vast majority of the application, just like our brain, we probably don't need to keep a lot of information for long duration of time. So it's all about like, you want to store it temporarily, you want to process it and move to the next thing. So a large majority of tasks is like that. And then few of those tasks where you want to keep it for long period of time. And even in that long period of time, you would want some of them to be raised over a period of time and keep something. So if you are looking at like creating a natural energy efficient like way of processing things, like analog memories could be a way to go ahead. And overall energy that you could save is much more because you could do volume processing, you have 3D integration and other ways in which you can go about like packing more and like, storing more. Now, out of like various different like analog systems that you can build, like one of the approaches using like memories itself, like, and in that memory category, like memristors are one of the promising category of devices. So memristor as such, it's a very, the theory of it has been around for quite a while from early 70s onwards. And many things or many properties have been like discussed in the literature over the years. And every device that claims to be a memristor, one thing that you have to realize is it may not be having all the idealistic properties that one would imagine. So some devices would have certain properties, some other devices would have certain other properties. But there should be some very basic kind of like properties that you can call the device to be a memristor that needs to be obeyed. And beyond that, a lot of the other properties that you would see that may vary from one device to another. Now, one few things that you could look at, like the dynamics of the device itself, is extremely like interesting. Like you can create a whole definition of complexity through edge of chaos, and looking at the equilibrium points and other things. You could generate patterns. You could create different kinds of filters. You could, all with like a set of like a few memristor devices, you would be able to do that. Then in special arrangements, like in crossbar arrangement and others, you could actually build like analog MACs. And these are again like one of very important things for applications that you could see. And another aspect that you would see is like it can enable a wide range of like compute methods, like in-memory, stochastic, hyperdimensional, cognitive, neural, analog, etc. And some of the good concepts of sparsity and other things can be incorporated into the architecture. Now, the theoretical model that is out there, you can summarize a memristor into current controlled or voltage controlled device. And you have 4 levels of hierarchy at which you can look at, like from extended memristor to an ideal memristor. And you can see here dx by dt showing that's a dynamic behavior that you're seeing is a dependent dynamic behavior incorporated onto the device itself. So the state variable changes are one way to study this device more carefully and use its properties, those set of properties to create like systems. This is an arrangement of a crossbar. What you have here is a memristor and a selector device stacked together in a crossbar manner. So the currents here actually represents the weighted summation, the weights being that of the node consisting of the memristor and selector. And the inputs are the voltages. So using a weight and the output of these, or the currents here, it will be the summation of the weights and the voltages. Now weight here means it's just conductance of the memristor device. So which means like changing the conductance, if you are able to go and change the conductance of the memristor, you are able to program the weight. And in a sense, like a single column of the crossbar will indicate like a neuron in a neural network, and the entire crossbar simply resembles like a one layer of neural network. In fact, many different systems can be built with such an architecture. You can build various kind of neural networks. You can create memories. You can create analog and digital logic, various kind of logic circuits. Just like CMOS, you can create like memristor logic. You can use it for cryptography. You can use it for analog solvers. You can use it for image processing and so on and so forth. You can, in fact, like the idea is here, using those crossbar and using different ways, you can build all these applications on chip. At the same time, this doesn't come while you have like a lot of these possibilities. There are a lot of challenges as well. One of the biggest challenges is device-to-device variabilities and cycle-to-cycle variabilities that you would encounter. And there are so many of issues to be dealt with: the material stack, what needs to be selector switches, the high resistance and low resistance ratios, changes in operating voltages, operating current, endurance issues, temperature and noise changes. Then on the peripheral circuits, you would see all sort of things in a crossbar nodes: yield and redundancy, parasitics and IR drops. In the output side, of the crossbar, you would see sense amplifier, designing the sense amplifier and challenges associated with it, control circuits, the ADC, DAC, and other quantization techniques that needs to go in, the noise, the PVT and noise related things, and programming for the changes in non-linearity that one would observe in the devices. That's also like kind of like different challenges. Now, where we are today, if you look at, like, you would see the analog computing chips is still like at a prototype stage. There are some works that are happening. Whereas if you see the sensors and CMOS, they are all like product stage, right? So the memory systems today, like, they are mostly in an MVP stage, you can say. So people have shown like chips which works. The concept is proven in many ways, but the question is, can this be taken to the product stage? And that's what, like, people are trying to see for the robustness. The product engineering itself, like, is being like discussed and improved. So it's an example, like, if you see here, this is a generatory adversarial network, GAN, otherwise, which we implemented on a using like Memristor systems. You can imagine the complexity, like each one of these blocks needs to be like, it will resemble something like this. And several of such blocks needs to be put in together. And you need to ensure that, like, this is something that's trainable, that works. So with again, like, the generated images looks like this. Now, the advantage you have by doing this in a chip rather than on a large server is that the training, for example, which took like 20 days in a server, equivalently, we could do it in like in a few minutes. So there is a lot of advantage on that front. And the second part was mainly like the whole when you are trying to design something specific, you can very easily go and optimize for the area, power, and things like that, which typically, like, when you run it over a cloud, you will not be able to do it because you're using a generic system. Another kind of systems that we try to build over the years, this is like HTM, hierarchical temporal memories, and you also have like things which are more of traditional neural network, and the LSTM kind of like network, convolution neural network kind of networks, like, all those things can be like built out. Another kind of thing that you could that we were looking at is, okay, there is quantum systems as well, and how we can use the power of both quantum as well as a traditional like ASIC system. So the spiking neural network, we tried to put it on the CMOS side, and then we ran the learning part on the quantum. And what it did when we did such a system is the accuracies and things like this significantly improved. As you might know, SNNs are difficult to be trained directly. Whereas like with this approach, one could like train SNN with very high accuracy as well. Having said that, the challenge here is the quantum errors. So if you have like large quantum errors, it's still like a bit of challenge. So reducing the quantum errors is one of the open problems that one would need to address there. This particular work, what we did, we found something very interesting, that like there are a lot of non-linearities and other things that usually come up with multi-level memory systems. So how do we build like highly accurate like weights? So we just connected the rows together and found like many interesting things that was happening around when we do that. For a start, like getting around the math of it was a bit tricky. It was showing cyclical number patterns when you do that, especially you take like 8 layer, for example, if you take a 8 level memristor, put both of them together, one would see that eventually you can get around more than 50,000 to 60,000 states out of it, which was interesting. And it could replace like many of the systems which had like trouble. Another thing that we looked at is, okay, this finding the right kind of networks or like the hardware blocks to design such systems are quite challenge. So how do you go about doing that? So, so if you, how do you reduce the complexity of the designing process itself? So instead of a human being sitting there trying to optimize for each of the designs, like what we did was we used like a genetic search, multi-objective search to find what hardware blocks are best suitable for optimal for like a particular area, power, and other aging and other things, along with like the accuracy one would get. And by this, like we could optimize not just the hyperparameters, but also the selection of the device, and kind of removes the need to have like a extensive need to have like analog designer to sit and figure out like how to place all these things together to form the architecture. So the architecture was automated, and it seemed to solve a lot of problems with device failures and others that would come in as well. Another work that we recently show was this one where showed like something for braille character recognition. Like there was one possibility to integrate sensor along with the resistive system all together into a single cell, and we could see like with a 3-layer ANN integrated into like a touch sensor. One could recognize braille characters with a very high accuracy. So this kind of shows like how neural like analog systems can be integrated along with the sensor and still be able to perform at a very high accuracy without the need to have like complex systems like large like digital chips or like FPGAs around. You can actually build like something at an extremely like low power and component requirement. Some of the other algorithms or the applications that we have tested our systems. Some of them include like high insulator monitoring, drone systems, wireless charging, for autonomous driving, for security in consumer electronics. And also as a accelerator, some of these prototypes and systems were tested along with some of the companies to see the commercial feasibility. So if you look at like the overall like compute ecosystem in analog, I would say analog can be there in any part of it. So it's time that we think beyond digital in all these things, because there are a lot of places or applications where you can bring in like analog computing, whereby improve the overall system efficiency, compute requirement, and all those things. So the whole idea that analog is something special goes to only say near to the sensor alone is something that needs to be I think like broken to create this like ecosystem. And there are a lot of compute ecosystem where analog computing can be useful and will be useful as we go along. So neural computation definitely is one thing. Quantum anyway has like a lot of analog portions going into it. The cryogenics, electronics, and all those things, like there are a lot of analog computing there. Probabilistic computing systems, a few works in that direction. In memory, many works are there in that direction. And then you have like a combination of analog and digital. That's something that's obvious to be put into across like both. So from the computing, how the communication happens within such systems, you can think about like for efficiency purposes, thinking about spiking signals, you can think about discrete pulses or like optical signals, all of which would be quite useful approaches to think when combining with the analog computing cells or units. Thank you. So if you have any questions, I'm happy to take it.
Participants, if you have any questions, you can ask.